we can have the panelists' videos pinned up. So today's panel is, it consists of three people who are both closely related to this work from different directions. So Madhusudan was one of the primary architects of the PCP theorem. He's currently at Harvard. He did his work on the PCP theorem while he was a PhD student at Berkeley. So welcome, Madhu. And then we have two mathematicians. We have Marius Junge, who is in the mathematics department at UIUC. His work is on, he works on functional analysis and C-star algebras. And I think he was involved in the proof showing the equivalence conjecture and Kahn's embedding conjecture. And then William Slofstra, who is at the University of Waterloo. He works on the mathematics of quantum information and quantum computation. And he's extensively studied questions about the value of entangled games and Zirelson's conjecture. So welcome everybody, and maybe we can start with a few, just a 3-4 minute comment by each of you about Henry's talk, and also about these. As Henry said, there are many different directions from which to look at this result. So, please do look at it from, the directions that you would like to. And so, maybe Madhu.
Sure. I don't know if I have 3 to 4 minutes worth. It could be an hour or it could be a minute. We'll see how this goes. So first, I want to echo what Scott said in the chat already. It's a really beautiful talk, and thanks very much for giving us intuition into why we're getting this squeezing happening. Few quantitative-ish questions about the talk, so maybe that's the way I want to think of it. You talked a lot about the verifier's complexity. Did we speak at all about the communication? How much communication was there between the verifier and the provers? So maybe I'll you can batch process the answers. So I'll ask a few questions that I have, different directions, and you can give me a sense about the answers later when you get a chance. A second thing was we talked a lot about this low degree testing. In the world of computer science, there's a much simpler test, the linearity test. It's sort of more basic, has the same quantitative effect that you ask very few questions and verify properties about some growing object. Would that have been good enough for you to do your entanglement testing? Or did you really need this low degree test? Was there something quantitative about the difference in these parameters which makes one work, the other doesn't work? In general, if you had to choose the two parameters, how many variables do I have and how much degree of a polynomial do I want to work with? Is there some trade-off between the two that makes things work? Finally, this magic square property, it's really very intriguing to me that you're sort of putting a magic square property on top of a low degree test, whereas I think of the low degree test as sitting on top of a magic square property, which is a very different magic square, but somehow the very idea that you sort of ask questions along one line, a different line, and then you look at this two-dimensional plane spanned by these two lines and see that there is some sort of a consistency that you're asking for. The lines in one direction should all form polynomials, and that implies that the lines in another direction will form polynomials. So there's I don't know if there is this magic square properties inherent to your, could you have worked with any locally testable code, or did you really need a locally testable code which was analyzed using this property? Okay, so that's probably the kinds of things that I had in mind. I'll let Umesh decide.
Okay, so it's very appropriate, Madhu, that in keeping with interactive proofs, you chose to make your role on panelist as being interactive with Henry. So Henry, do you want to respond to all these comments? They're really good questions.
Yeah, I can try to respond. Also, I noticed that, Toman, John, and maybe Anand are on, so please feel free to jump in. Your first question was complexity versus time complexity versus communication complexity. The communication here we allow to be as up to the time complexity. So if it was polylog t is the time complexity, then that's the amount of communication that we allow to go back and forth. Let's see. And then you're asking, what about a simpler test like the linearity test? And I think actually to get there is an entanglement test based on the linearity test that I think Anand and Toma developed this earlier called the polybraiding test. And it's very robust, but in order to certify, let's say, n qubits of entanglement, then the communication complexity has to be n. So there's no savings. So somehow it seems like increasing, allowing the higher degree is useful. You're asking what degree is needed, and actually not constant degree is fine. So like 3, I think, is fine. So it doesn't need to be very, very high degree, but 3 is enough to get some saving. Well, I mean, actually, to go from polynomial to polylogarithmic is overkill in the sense, because once you can just get a little bit of savings, you can just recurse and as many times as you would like. Yeah, and then you had a question about the magic square game versus the low degree test. Actually, I don't know, maybe John, do you have any, I know you've thought about this. I don't know, John, are you listening?
I'm listening, but I don't really have a great answer. As far as I can tell, they just both happen to involve squares, but 2 different squares. I did spend quite some time actually trying to see if you could compose them in some way that created a more beautiful object that wasn't just these 2 separate tests. And I never really got anywhere, but I think it remains an interesting open question. I don't know, Anand just appeared, so maybe he wants to step in and answer this as well.
Oh yeah, I guess the one connection is we were thinking about ultimately we have to use the axis parallel low degree test. And then we had to add this sort of annoying subtest uniquely for the quantum case where you pick not an axis parallel line, but a diagonal line, and you check for commutativity of measurements along the diagonal line. And then you might ask, is this test strictly necessary? And that's a case where the 2 notions of square actually match up. So you can say, yes, it's necessary, because otherwise you could do something magic square-y, where the axis parallel lines commute, but the diagonal lines don't commute. Yeah.
Okay, Anand, while I have you, can you just comment then, if the axis parallel line was important, how is it that the linearity test manages to work?
Oh, I mean, the linearity test is testing all possible lines, right? So you're, in particular, you're certifying that all pairs of observables commute, right? Because you can fit a line through any pair of observables. Yeah.
I mean, strictly speaking, I think the standard low degree test also works, but the way we analyzed it was using the analysis of the axis parallel lines test. So since it was easier to analyze it that way, we just phrase it in terms of that test. I think you could also just get it for the standard low degree test. You would just not get the standard low degree test soundness. You get the weaker axis parallel lines test soundness.
Thanks.
Great. So Marius, would you like to?
Oh yeah, absolutely. So first of all, I really have to thank this crowd for solving this problem. I mean, you have no idea what that means to us, right? I mean, I'm coming from operator algebras. I have talked to experts in this field, and they told me in the morning they believed con-embedding is true, and the afternoon they thought it's false. But some days it was the other way around. And I cannot give you the name of the person I talked to. It would be, breach of confidentiality. But that was the state of the art before William and you guys entered the scene. So the point is that the conjecture was not even formulated a conjecture. It was kind of a side remark. We don't know, and then evolved of one of these problems where simply we had no idea what's going on. And of course, your proof is in some sense a blessing and a nightmare. The blessing because the answers, the question is answered, and we now know why it was so hard to deal with this for such a long time. And it's a nightmare because our techniques simply don't shed any light on, why this is true or not. I mean, I think that's a big open gap still to be filled, right? Often people associate con-embedding problem with this problem. The name which should come up just as a matter of fairness is Kirchberg. He made the transition from this hyperfinite von Neumann algebra language to the group C star algebra language. And the group C star algebra language gives then the transition to these finite state configurations. And that is the connection to there's a direct connection to these parameters encoded in two-player games, right? So that is the history. And in fact, the discovery was exactly like this. Werner Scholz gave a talk on the Saracen problem in a quantum conference, which I happened to visit because I was interested. And after the talk, I said that's con-embedding. So it's really, if you know the parameters, that's not it's pretty easy to see, but it really follows from Kirchberg's work. So these are the things I have to say. And it appears that this recursive idea which you use, right? I mean, to go from one set of games to another set of games, that is, I don't know, for me, that is a real mystery, right? So that this is effective in this background. Of course, I know that there's, PCP tradition. There's a lot of tradition on the computer science side, but that is still completely mysterious. That, I see the power, but I don't understand it in my bones, why this really makes a big difference, right? So this is unbelievable. It's would be out of sight from our perspective. Yeah, and then I want to thank you. You essentially answered my intermediate question with a picture, right? I mean, you have these, you guarantee a lot of entanglement, but you only test it in a few coordinates, and that means you can use the rest of the entanglement to do whatever. And that answered my question, which I had in the beginning, which makes it a little paradox, right? I think this also answers some of the questions of, whether randomness is preserved or entanglement is preserved. I think you have to just preserve both, right? In your inductive procedure, you have to just, if I understand it correctly, right, you have to preserve both parameters in a reasonable way. Yeah, these were my comments. The only question in terms of, verification is, it would be nice if there were a joint effort of transforming your proof simply in the language of operator algebras. And I think you can appreciate because you went the other way around. Trying to read our papers and translate it into complexity questions. So I think if there is some effort underway, either you don't have to answer publicly, but it would just be very, very nice if somebody is on that and could write a paper which is just accessible to both communities. I think that would be a great service, now where we are probably certain that it's true.
Great.
No, I'm sure you're right, but people have this trust issue because they cannot understand the other way of reasoning because they have not inhaled this for 20 years, right? So it's understandable, and I think you can relate because when you first saw the C-star proofs, you probably had the same feeling. What on earth are these people doing, right? So that's probably an experience we can all share.
Thanks, Marius. So actually, just a very brief follow-up question. So given, given the success of these methods at this particular problem, are there others? Are there other questions in the neighborhood that you could you
Oh
might
yeah,
see?
sure. I mean, in geometric group theory, right? This problem about Sophic groups, right? Or William, you probably know this better, right? So so the question is very, I mean, hyperlinear groups. Every group is hyperlinear was the question. So we are asking for, you know, they solved the problem for certain C-star algebras certain objects in our class don't have that property. But it would be nice if it's not solved for, there exists an object which has that property, but there exists a specific object associated to a group which fails that property. So I think we have some experts here. The first step in doing this, it would be to verify that all the games you use are synchronous. That would go in the right direction. And I heard rumors that you guys know that. It's just that I don't know it. Right? So that would be a first step. So if all the games which occur here are synchronous, that would, after the work of Paulson, at least indicate that maybe this is really a group solution. And then this would solve other problems related more to geometric group theory, or this intersection of geometric group theory and operator algebras. That's one. I think William probably knows more about this than I do, but yeah, the other open problems. Well, there's this big open problem about group isomorphism, right? Whether two free groups have the same von Neumann algebra. If that could also be handled with this problem, this would be, of course, a nightmare for operator algebras, but of course, fantastic, right? So there are problems which, if you can transform this into a purely group theoretical result, they would be not in the vicinity, but, you know, at least in a large neighborhood. Mm-hmm. Yeah, so there's hope that this line of research can provide more theory, and there's also the group in continuous logic, which already has a lot of reformulations of your result, right? So this, there are some community who are already experts on this already.
Great. So, thank you. William?
Yeah, so I want to say as well, I really enjoyed the talk you gave, Henry. So, you know, non-local games for the past couple of years. So I had kind of had a front row seat to seeing MIP star equals RE being proved by Henry, Thomas, John, Anand, and Zhenfeng, which was a real pleasure. My own interest in it came out of wanting to know the Searleson problems, what the answer to those were, mainly because, I mean, it's a really big, important question scientifically, but I read Searleson's original papers, when I was a grad student, and I just loved them. And then, of course, there was this mistake in them that was found by, I guess, first Miguel Nevesquez, Peronio, and Athene, and then led, I guess, into the paper that Marius wrote about its connection with Kahn embedding, and I just kind of wanted to know what the answer was to this this conflict with this paper and the work that he'd started. So it's really nice to resolve that. And I guess the question then, which maybe when we have a panel with kind of multidisciplinary experts together is kind of interesting to talk about, is where do we go from here? And from my point of view, I've been getting more and more interested in kind of the algebraic side that Marius is talking about, the connection with Kahn embedding and so on, and especially the part of what you might call approximate representation theory, which is, I think, really maps exactly onto what Henry was talking about non-commutative property testing. So I'm glad that has come up. The questions there are essentially when you start thinking about algebras, so you have generators and relations, and you want to understand their representations in matrices or maybe in operators on a Hilbert space. But then maybe you want to be a little less strict about it, as often happens in something like quantum information theory, where you have noise. You not just say that the relations hold, but you have the relations hold up to epsilon. That's what you call approximate representation theory. So the Kahn embedding theorem is really fundamental for that. it says that you can have algebras. And I think, Henry, maybe you better jump in and just double check that I'm right about that. But you can do it with synchronous algebras in your paper, right? They're synchronous games. So you can write down specific. Yeah, so you can write down specific algebras where you can't. You can have something in the algebra which is non-zero as an element of the algebra, or actually even more relevant, you can have a tracial state on it which shows that thing is non-zero. But then there's no way to actually approximate that and see that that is non-zero with finite dimensional approximate representations. So that's the kind of the core application of this of the MIP star equals RE to approximate representation theory. But then we get a lot of interesting things that come out of that. I don't think the story is over at all. Maybe the most pressing one is Marius said, it's just can we find a translation of the, so we know that a lot of questions about non-local games translates into questions about algebras. And so can we take the MIP star equals RE proof and put it in terms of something that's entirely in terms of algebras? I think that would be really nice to help the broader mathematical community digest the result. And Henry, I know you've mentioned working on stuff like that, so that might be kind of interesting to hear about where the standing of that is. But the other really interesting aspect of it is just once we start combining these two areas, that it suggests new research problems. In particular, bringing in ideas of efficiency into approximate representation theory, just thinking about like how do stability questions change, or what kind of new stability questions do we get when we start thinking about how we trade off number of relations versus the stability constant, and stability constant, how close do we have to actually, so stability question is where we say something like, you have an approximate representation, is it close to an actual representation? So the stability constant or constants would be how close do you need to be, and then how far away do you end up being? How close do you have to be before the result kicks in? That would be like your threshold in the in a PCP for how trying to pass the test, and then how close do you end up being? That's your delta in Henry's talk to the actual to the exact representation, and then your efficiency of the verifier, I guess, would be something like the number of relations that you need to consider in your algebra. But there's maybe a couple different things you could put in there. So I'm not sure we know exactly what the most interesting way to ask the questions are, but clearly it's really the crucial, or one of the crucial issues that come up in the MIP star equals RE proof. And so we should be kind of studying questions around that. And then there's also the question of descriptive complexity, which is how, when we look at a proof of MIP star equals RE, how complicated do the proofs have to be? And so can we prove them in particular with what are called linear system games? That matches really well onto a question of, can you have a non-hyperlinear group, which we'd like to have on the algebraic side, which is not to just say any old algebra that has this finite approximation, does not have this finite approximation property, but specifically a group algebra, which does not have this finite approximation property. So I think there's just a lot of interesting research questions that come out of this that will be interesting to see what happens with those. And I'm kind of curious to hear Henry and other panelists' thoughts on where that might go. Oh, I should also say, while I have the mic, just that Marius, I think I was a little too strict on what I said with property T. So the actual result, it's nice to be able to just Google things while you're at a talk with this online format. But the actual result is just some of the common property T groups. If you know that they're hyperlinear and property T, then they can't be stable. So I don't think it's kind of suggestive that maybe we don't know how to combine stability with property T. You probably know the same result, I'm sure. So then, but it's not a very strong obstacle to trying to find some connection to property T with MIP star equals RE. Anyway.
No, I think it's often more the spirit, right? So I mean, I think that's in fact one of these very important concepts used, is that there's some kind of rigidity. If you are very close to a certain, if you can verify that a certain configuration happens with large probability, then the whole algebraic setup has to be very close to the group which you had in mind in the first place, or to the algebra which you had in mind in the first place. So this is really saying that finitely many conditions up to epsilon guarantee that you have almost an infinite dimensional amount of information at your disposal. And that's I mean, your work does verify that in a certain sense. All the rigidity results verify that you have a lot of entanglement. So many of these generators have to commute. They have to look in a certain way. So these are all results in this direction, which are but used as technical tools, if I understand it correctly. But this phenomena is, of course, interesting for other applications.
Yeah, I totally agree. It's kind of the zoomed out level of how does how does this interact with the stuff we already know in algebra, like the property T stuff. Be really interesting to see how it kind of connects.
Great. Well, thank you, William. So, Henry, would you like to add your comments?
Yeah, I guess I don't have so much of a comment, but more questions along, because I'm not very familiar with what's going on in approximate representation theory, but when I hear about it, it sounds very familiar to these questions about like property testing. So like, I guess one question I have is, in approximate representation theory, it's you have questions about robustness. Like if you have something that's close to a representation, can you round it? But it doesn't seem like there's considerations of efficiency. Whereas in the property testing world, efficiency and robustness, like the trade-offs between the two are very important. So just as an example, like I think like Madhu brought up linearity testing. So let's say you have a Boolean function and you want to test whether the function is defined over the hypercube, and you want to test whether the function is close to a linear function. So you can do this pretty robustly, but trying to develop entanglement tests based on it doesn't give you quite enough to get somehow the complexity. You're not getting any savings in complexity, but you're getting robustness. Whereas with the low degree test, you're getting something extra, and due to some efficiency gains. So I guess my question is like in say approximate representation theory or operator algebras, are there any questions where people think about efficiency or?
I think that the phenomena I've seen are mostly related to robustness, right? So I mean, the easiest thing is you have a certain number of operators, they have an almost fixed point, right? Can I show that the whole group of operators has a fixed point? So this is robustness, right? I check with finitely many conditions, and then I can guarantee that all of these guys leave a certain vector almost invariant, right? So that's the idea of Kashtan property T. This is all about robustness, right? And then there is an epsilon delta relation. Now I don't even know where the complexity would come into such a question. I have not even seen a formulation. So I think that's something which was not on our radar, right?
Interesting.
But of course, if you write down a proof for, if this happens, then that happens, then of course you can maybe add other aspects. Or I think what happened in your proofs a lot is you have, two pairs of configurations, and you want to go from one configuration to the other one. If this group has Kashtan property T, then that group has Kashtan property T. And you want to, or if and only if, and you want to relate the two. Maybe that is, that is this descriptive part, which I've never seen. I mean, I have never seen anything like it, right? I mean, because these are existence proof, right? For every epsilon there exists delta. So I maybe this is hidden in these kind of, if you prove it, you might have some aspects of what you're asking for, but it was never considered to be relevant. But that is, as you know, it's a tradition, right? I mean, we look at things we know because we have learned them. I mean, so that this is relevant was just never brought to our attention, period, right? At least from my perspective.
I mean, based on, I guess just from my own personal opinion about sort of what's the real technical core of our proof. You know, the recursion and things are kind of nice, but really the most difficult part, I think, is actually analyzing this classical low degree test in the presence of quantum provers. And somehow that, to me, that's like the most mysterious thing. I mean, even in the deterministic case where there's no non-commuting things going on, even the classical proof of the low degree test is quite non-trivial. And to me, it's very mysterious. Madhu probably has better intuition about it, but anyways, that's just my.
Yeah, and that's something which I learned today from your talk. This was clearer than in the talks I've seen before. So thanks for that.
Henry, could you clarify low degree test versus low individual degree test and the subtleties there?
Oh, yeah, it's just different definitions of when you're counting degree of a polynomial. Do you just look at the total degree of all the exponents in a monomial, or do you count like the maximum degree of any variable? And so those differences, so there's different flavors of low degree tests, and you get different parameters, and we can analyze just one of them, this low individual degree test.
Great. So maybe we can move on to audience questions. Adam or Chinmay, do you see any?
There was a fairly long discussion in the chat about how to go from your talk, which was about T-bounded halting problem, to the complete halting problem. So maybe if you want to say a couple sentences about that.
Oh, right. So essentially, it's, I guess the way that in my talk I presented sort of like a top-down, you start with T and then you want to get the verifier as small as possible. But actually the way it really works in the MIP star protocol is the verifier has some fixed amount of time, and it asks the provers to continue going upwards to keep on generating larger and larger proofs until it has a proof of that it halts in some finite time. And only the provers know how much time that is. But the result of the interaction is that the verifier knows that all of these proofs have been recursively connected in the right way down to the very bottom. That's just the high level.
And obviously without knowing how long it took.
Right.
Any other questions?
No, I don't see any. Adam, do you see anything different?
Can I ask a question, even though I'm a panelist?
Yeah, please, of course.
So, Henry, I'm just very intrigued by this entanglement test that you have. And I know I've asked some variant of this question to Anand before. I wasn't savvy enough to understand the answer then. Maybe I'm better now. Is it the case that if I want to prove that I have at least, if I want the provers to convince me that they have at least A bits of entanglement, or in other words, soundness condition is if they have A bits of entanglement and less than A bits, they should not be able to convince the verifier. I'm happy to require them to have a huge number. For every A, there exists a B, such that if they have B bits of entanglement, they will definitely be able to convince me. And I'd like to know, can I do this protocol with a constant number of bits of communication, independent of A and B?
So A and B is the gap, I guess?
Yeah, for every A, I want to show there exists a B, such that distinguishing between having at most A bits of entanglement and at least B bits will require constantly many bits of communication. The constants are independent, so there exists a universal constant such that for all A, there exists B. Is this true? Is this not true?
Sorry, how would you show the at most B?
Sorry, I don't want at most B. I want at most A. If they have at most A bits, then I don't want to be convinced. If they have, but to be able to convince this protocol, they might require at least B bits. Okay.
So, I mean, there has to be some dependence on A and B, and I think, roughly speaking, there should be some protocol that depends on, I guess, the Kolmogorov complexity of describing A and B, or at least the gap between them. Then there's some protocol whose complexity and communication depend on their description lengths.
I see. So if I fix the constant, then you're saying there's only some finite constant amount of entanglement that I can verify out of it. And how does this all work when Kolmogorov complexity is itself sort of not an absolute thing? It depends on my encoding of Turing machines.
Right. Well, because I guess in these proofs, you're choosing a particular way of encoding Turing machines.
Okay, so, all right, okay. So it's not like there's another universal constant out there that I've missed. Okay, you're saying it's going to depend on A and B at some level.
Right.
Great.
Thanks.
Is there time for another panelist question?
Oh, definitely, yes.
Because I really want to know, maybe for Henry and other authors here, or just anybody, what are the process? I think this is relevant to the question of, can we make a proof that would be more digestible to a broader range of mathematicians, let's say? What are the prospects for proving, for disproving Conn embedding without something like the low degree test? Is there any hint that we could just do it entirely without it? Like, that would be the counterpoint to saying we should really start thinking about efficiency questions in approximate representation theory. If we could just take it out entirely, then maybe we don't need to do it.
I mean, I've been so steeped in it that of course I don't see a way around it. I guess one thing I can say is, if we don't use the low degree test, we use something simpler. Like, instead of using PCPs, we use something, the precursor to PCPs, which is the Cook-Levin theorem. Like, this is a very efficiently checkable proof, but it's not very robust. Then we can actually use something, the proof becomes much simpler, and then essentially we can reprove your result, where you separate you show that computing the value of non-local games exactly is undecidable.
What do you think about trying to do, because you could try and do, because it's also the case, like the low degree test really helps you get the gap that you need in MIP star between, between being able to satisfy to prove it when you do halt and fail when you don't halt. But you also have proven for 3 players that if you don't have a gap, then checking whether or not you have a, let's say a well, okay, we don't have the result of that, but we could say something like if we could show that if you could, checking whether or not a synchronous game can be played perfectly in R omega, if that is pi 2 complete, that would disprove Conn as well, right? And it doesn't involve a gap. You don't need to know anything about a gap there. It's just a gapless question. But the proof that you have for 3 players that you can do this with, not for synchronous games, but for 3-player games, uses the MIP star equals RE as a black box. So if you could somehow just jump directly to proving that, maybe you could take out.
Right. So I guess one thing is, like, now we know that that can be done with 2 players. So like with synchronous games. But yeah, you're right. It's interesting that even to prove a gapless result, we still need a gap in the middle. Yeah, I'm not sure how else to get around it. But.
So actually,
maybe it is worth mentioning that, of course, there were other variants of the Conn embedding problem, not involving two parties, but multiple parties. And at some point, from an operator algebra point of view, unfortunately, it wasn't clear if you disprove it for 5 parties that you automatically disprove it for 2. So that probably, I would have suspected, that disproving it from more parties is easier, but it turns out that that was not such a big difference, right? I mean, simply because the complexity of the proof for more parties is harder, and then we know fewer things to do, or they know fewer things to do. So that's very interesting, but I mean, somehow with the negative solution, these difference between multipliers and 2 players on that question is washed away. But it's super interesting whether in some other context there is a real difference between multiplayer protocols and 2-player protocols. And maybe there are some, even some applications in finding extremely nice multi-layer entanglement tests by such an inductive procedure. Who knows? I mean, so I think from a quantum info perspective, this also opens a lot of additional questions. But I'm not an expert there, but I suspect Henry knows much more about how to rewrite this into a protocol which is really convincing another person that we have the best quantum computer in the world, right? Loosely speaking.
Loosely speaking.
Yeah, the 3 versus 2 question, is that still for proving pi02 completeness? Is that still open, or?
I think yeah. I mean, that's something that is being written up. So
okay,
yeah.
Maybe I shouldn't have asked.
No.
Yeah. So well, this was great. Actually, just for completeness, Henry, let me could you comment on the relationship of MIP star equal to RE to the quantum PCP conjecture, at least the games version of it?
I can say something, and again, I probably, I think Anand should feel free to comment because he's worked on this for a while. But I believe that it depends on what you mean by the quantum PCP conjecture. So there's 2 variants. There's the games version, the local Hamiltonian version. For the games version, you can ask, one way of formulating is that it's QMA hard to decide the value of a non-local game, or approximate it to within some constant. And that, strictly speaking, is implied by MIP star equals RE. I mean, it's not just QMA hard, but RE hard. But one thing that's missing from that is, in order for the prover to convince you of a QMA hard language, they need to essentially solve the halting problem for as far as we know, or maybe not the halting problem, but say something that we believe to be much harder than QMA. So you can ask if you had a quantum prover who only has QMA power, like they get some quantum witness and they just want to prove to you that this witness is say the ground state of a local Hamiltonian, can they prove this to you with a constant gap? And that's still open.
Great. So, well, let's, this was really fascinating. It was a great talk, Henry, and a wonderful panel. So thank you, everybody, and also the audience for their questions. So let's see, we can continue to our discussion on GatherTown. So I've posted the link there, and next week we'll have our last quantum colloquium for this semester. We'll take a break for the summer after next week, and then resume in the fall. So next week it's going to be Ronald DeVolf, talking about quantum optimization. So, so thanks everybody, and see you on GatherTown.